That for phi, a normal positive form, or even for an NSF weight, the following things are equivalent for an x in M. The first thing is that sigma t phi of x is equal to x for every t. This is the same thing as phi of x a y. It's equal to phi of y x for every y in M. And if we want to have an NSF weight, this means that x m phi is included in m phi, and m phi x is included in m phi, so that these two things are equivalent. I stated it for NSF weights, but I will do everything just for normal positive forms. Now, having this thing, and the KMS, also the KMS condition, KMS characterization of the modular automorphism group, I will state and prove here the cocycle theorem. I like to call it also the Radon-Nikodym theorem, because this is actually the most general Radon-Nikodym type theorem. And the situation now is the following. You have M a von Neumann algebra, and you have phi m psi, two normal positive forms on M. Then you look at the algebra P, which is the matrices 2 by 2 on M. This contains an X, which is a matrix x11, x12, x21, x22. And among the elements here are also the elements E11, the matrix unit, which is 1, 0, 0, 0, and E22, which is 0, 0, 0, 1. Okay. And now we define a normal weight or a normal positive form on matrices 2 by 2 in the following manner. Tau of x is equal phi of x11 plus psi of x22. And it's easy to see first that this is a positive form, because if x is positive, the x11 and x22 are necessarily positive. So that, and the normality also, it's easily proved. Okay, now look at this thing. You have x times E11 is what is x11, x12, x21, x22 times 1, 0, 0, 0. So this is x11. Here is x21, 0, 0. And the same result you obtain if you make E11 x. And then you take the theta of this. It's equal theta of x E11. Namely, everything is phi of x11. So that it follows that this E11,
You mean E11 on the left side?
sorry?
The second,
Yeah, of course. E11 X, thank you. This means that E11 belongs to the centralizer of the algebra P theta. The same way you see that E22 belongs to the centralizer of theta on P. So that we have the following thing. If I look at sigma t of theta of x 0, 0, 0, I see that this is equal to sigma t, tau, theta, of E11, x 0, 0, 0, E11. This is equal to this. But sigma t is an automorphism, so is equal to sigma t of E11, which is, let's put it, sigma t of E11, sigma t of x 0, 0, 0, sigma t of E11. So because these are in the centralizer, this is E11, sigma t theta of x 0, 0, 0, sigma t of E11 is E11. So that this matrix here, 2 by 2 matrix, which is here, satisfies this equality. This means that necessarily sigma t of theta is of the same form. Here is 0, here is 0, here is 0, and here you have, say, a sigma t of x, which is just a notation for the moment of x11. Okay, sigma t of, okay, it's just a notation, sigma t of, say, of x. Okay. But now, you have the KMS conditions here of sigma t theta, and from the KMS conditions.
on the left side, you don't have any argument. Sigma theta t of
Here, you mean?
left side. Left side, sigma theta t.
Yeah. Sigma t theta of x11, 0, 0, 0. So that here I have something depending on this thing, so of x11. That's okay, thank you. Now, this satisfies the KMS conditions with respect to theta. Theta is this thing. So we infer immediately from here that this satisfies the KMS conditions, so sigma t satisfies the KMS conditions with respect to phi. It's just trivial to see this thing. So that actually this one is exactly the sigma t associated to phi. So that what we have that sigma t theta of x11, 0, or just x 0, it's equal to sigma t phi of x 0, 0, 0. And exactly the same way, you get that sigma t theta of 0, 0, 0 x is equal to 0, 0, 0 sigma t psi of x. Is exactly the same argument. And now it remains to look at sigma t theta of 0, 1, 0, 0. and to see what happens with this. With the same kind of an argument, you see that this is of the form 0, 0, 0, something here. You multiply by E11, E12, and so. So that this thing here is something u depending on t, which is here, 0. Okay. Now, we have to see what are the properties of ut. First of all, the first property is that the map T goes to ut is an SO continuous. Since the map T is going in sigma T theta of 0, 1, 0, 0, is SO continuous. Yes, SO continuous. The second property is that ut are unitaries. And this will be seen in the following manner. I look at ut star, ut, and 0, 0, 0. And this is equal to 0, 0 ut star 0 star times u0, 0 ut 0. That's obvious. And this is equal to sigma t theta of 0, 0, 1, 0, which is star, times 0, 0, 1, 0, which is in here, which is sigma t theta of E11, which is equal to E11. That means it's equal to 1, 0, 0, 0, and hence here you have 1. And the other equality ut star is equal to 1 is obtained exactly the same way using E22. That's so the third thing which appears here is that u t plus s is equal to ut sigma t phi us. This happens for every ts in R. The checking of this is similar because you have the following thing: 0, 0 u t plus s of 0 is equal to sigma t plus s of tau of 0, 1, 0, 0. This is equal to sigma t tau of sigma s theta of 0, 0, 1, 0. And this is equal sigma t theta of 0 u of s 0, 0, which is further equal to sigma t theta of 0, 0, 1, 0 times u of s 0, 0, 0. Okay, and this is clearly now is sigma t of this one, which is 0, 0 u t 0 times sigma t of this is of the form sigma t phi of u of s 0, 0, 0, and you end with this thing. It's u of t sigma t phi of us here 0, 0, 0. So that this guy is equal to this guy here, and we proved also this relation. The next property, 4, is that sigma t psi of x, it's equal to u of t, sigma t phi of x, or phi of x, u t star for any t belonging to S, to R. Okay, also this thing comes immediately. Let's put it there to be more clear. You have 0, 0, 0, sigma t psi of x. This is equal to sigma t theta of 0, 0, 0 x. This is sigma t theta of, you have here 0, 0, 0, 1. Here you have x 0, 0, 0. And here you have 0, 1, 0, 0. That's an elementary computation to see this thing. So that this is equal to sigma t of this, sigma t, I'm sorry, is 1 in here. Sigma t of this, which makes ut, 0, 0, ut, 0. Times sigma t of this is sigma t phi of x, 0, 0, 0. And this guy there, this one is just 0, 0, 1, 0 star. So it will give to you 0 ut star 0, 0. It's equal to, you multiply these matrices and you get exactly the fifth thing is that for theta, the weight obtained from phi and c, we have a KMS condition. This KMS condition will give a certain KMS condition for the UTs. It's not necessary to write it. It's just enough to know that there is a certain KMS condition for the U of t's. And with these 5 properties, the map T goes to UT, T goes to UT, is unique. With these 5 properties. The uniqueness follows from the KMS condition. This is the main thing that ensures the uniqueness of such a map. It's not necessary to go into the details here, because it's obvious that, and it will take 1 hour to write on the blackboard. Okay. Now, this unique map associated to 2 weights, phi and psi, it's denoted by d psi divided by d phi t. This is ut. And as you see, ut is SO continuous. ut are unitaries, but it is not a group of unitaries, it is a cocycle. That means it satisfies this equality. Now, if it is ut plus s is ut times us, if it happens to be so, then U is an isocontinuous group of unitaries, so U of t will be analytic generator power IT, and then we expect that psi should be something connected with phi and with A. It will be actually something like this. Phi sub A of an x will be phi of A power 1/2 x A power 1/2. And not exactly this, but you put the spectral projections En here, and you take the limit. But what I say is just that you expect such a thing. And such a thing is obviously a Radon-Nikodym type theorem. For that reason, this Kohn cocycle is also called the Kohn Radon-Nikodym derivative of psi with respect to phi. And that's all.
Are both the weights faithful?
Yes, in this exposition up to now, both weights were faithful. Normal semifine is faithful. But exactly now, I will say what means if the second weight, psi, is not faithful. Because even in this case, we have a Kohn cocycle. And we need to consider also weights which are not faithful. Namely, the first thing I would like to notice is the following thing. If you have sigma an automorphism of M, then you have sigma T associated to the weight phi tensor sigma. It's equal to sigma minus 1, composite with sigma T phi, composite to sigma minus 1. Sigma. This is checked.
So could I make a little comment on this? Okay. And the Radon-Nikodym theorem was at the heart of operator algebra.
No, but I will speak.
Okay. But what was missing during that period is the following. Okay. The people are trying to understand psi or psi for x in M. Try to analyze this. Everybody trying to understand this, including John von Neumann. But if you look at this 2x2 matrix, what we are doing is just to redo once again what Serban did for the single states. That's the 2x2 expanded to the exactly what's going on on the delta, etc. Then what happened is instead, this is the right thing to do.
So what? Watch. No, watch there.
How you find this thing in a natural way to,
Yeah. Let me make also a small comment, non-mathematical. Speaking about this result, Alan Kohn said, "This is the trick that made my fortune." Okay, so that this can be immediately checked using the KMS condition. So using the KMS condition, you check immediately such a thing. Moreover, M phi composite with psi, the centralizer, it's equal to sigma minus 1 of the centralizer of phi. And finally, again by the KMS condition, or just, okay, you have D psi composite with sigma, D phi composite with sigma, it's equal sigma minus 1 of D psi over D phi T. Again, this is checked using the corresponding KMS condition there. Okay, now I come to the question put by your colleague, namely that if you assume that psi phi is NSF, so it is fightful, but okay, it's a normal semi-finite for the normal semi-finite. The first question is, what means the modular automorphism group? You look at phi on the reduced algebra support of phi in here. And here, psi restricted to this is fightful. So that you obtain sigma T phi, T in R, but they are automorphisms of S phi, M, S phi. Now, how to do if you have phi a normal semi-finite and fightful weight, and psi just a normal semi-finite weight. Then the following thing, the Kohn-Cocycle theorem takes the following form. There is a unique isocontinuous map T goes to UT in M, SO continuous, such that you have first UT star is equal to the support of psi, which is equal to U0 also. Then UT star, it's equal to sigma T phi of the support of psi. Then the second property is that UT plus S is equal to UT sigma T phi of US. 3, U minus T is equal to sigma minus T of phi UT star. Fourth property is the same. Sigma T psi of X is UT sigma T phi of X UT star. And the fifth is a KMS condition. And this determines uniquely the cocycle in this case. So you see the support of psi appearing in the picture. Right. Now, the proof is exactly the same as in the fightful case. Now, what I will consider, what I'm saying is that to consider weights which are not fightful is obligatory for the theory. And we will see immediately such a situation.
I'm slightly confused. I thought only phi was stable. I thought psi was.
Phi is fightful, and
No, just below that view.
no, this was one thing, and this is another thing. So this was one assertion, and this is a completely different assertion, right? Well, you prefer I put psi here, but okay. So that if we consider V, we consider first phi and NSF weight. And we consider V in M, a partial isometry
I'm sorry, Serban. The second one, you're assuming they're both normal semi-finite?
No. Here I assume that one is faithful. Phi is faithful. This one is not necessarily faithful. It has a support S psi which can be strictly less than 1. Right? Okay. You have a normal semi-finite faithful phi and a partial isometry such that V star belongs to the centralizer M phi. Then we can define another weight, phi sub V of x is equal phi of Vx V star. And then the support of phi sub V will be equal to V star V. And using the KMS condition, we get what is sigma t of phi V of x. It's equal to V star sigma t phi of Vx V star times V. And this happens for x belonging to V star V M V star V and T belonging to R. Now you can wonder why is this. Is again the KMS condition that works and shows such a thing. In particular, you find that M phi V it's equal to V star M phi V. Moreover, for the conderivative, and you see now phi V is not faithful. The derivative d phi V over d phi t, it's equal to V star sigma t phi of V. Well, I assume that this thing can be verified also by the KMS condition, but in the papers, in the notes, you will have a direct proof of it. I will not bother you with the proof of this at this moment. So that the last equality there is proved directly. Yeah.
Number 4.
Yeah.
In that number 4, x should be inside the cut. I mean, x is not in M. X is in the...
Yeah, X is where C acts. So it belongs to S of C, M, S of C. Right, correct. It's okay. Good. Now, I have this thing, and I have a lemma. But in particular, let me say it. In particular, you can take E a projection in M phi. And what you get here, you get phi sub projection sub E will be phi of E x E star. E star is E. And what you get here, sigma t of phi sub E of x is equal E sigma t phi of E x E E again. And the derivative in here, it's constant. It's equal to E. Because this is E, and sigma t phi of E is in here. So that the derivative is always E. Okay, now, what I put, I consider phi an NSF weight, and V a partial isometry, partial in M isometry, such that f v star belongs to M, the centralizer of M, and also the initial projection E v star v belongs to M phi. Then what we have is the fact that you have phi sub v is equal to phi sub E if and only if V is in the centralizer of phi, right? Well, the proof of this lemma is the following. Suppose first that V belongs to M phi. Then you have phi of Vx V star, that means phi V of x. It's equal to, if it is in the centralizer, it will go in the other side. So that you will have, and also V, it's equal to VE, the initial projection of V. So you pass with this in the other side, and we get phi E, E is what remained here, and the E in here is V star V, which appeared. So that this was the proof in one direction. In the other direction, suppose that phi V is equal to phi E. Then phi of Vx, I will show that phi of Vx is equal to phi of xv. That means that V is in the centralizer. And this is rather easy to do. It is phi of the range projection of V times V, yes, x, which is equal to phi of Vxf, because f was assumed to be in the centralizer, so that it commutes with under phi. That means this is phi of Vx V star, V star, V star. Okay. And this is further equal to phi of well, what I do is the following thing. What I know is that phi V is equal to phi E, so that what I can put here, it's equal to phi of E. So this remains. And instead of V star, I can put E. So it's phi E x V E. Now, this is equal to, because E is in the centralizer, I can put it here, so that I have phi of x V E, but this is phi of x V, because this is the initial projection of E. So that this lemma is proved. And now we want to have the rules of computation.
For V to see that something the centralizer, you also have to verify the other conditions, right?
No, you have to verify anything else. You have to verify just that phi of xv is, of Vx is exactly equal to phi of xv.
I thought you also had a condition that x multiplied by m sub phi must be contained in m sub phi.
Well, that's okay. That's okay. I do the checking only for normal semi-finite functionals. So that, of course, in the case of a weight, but the proofs I do only for normal positive forms in order to avoid, I would say, artificial complications, right? So, okay. So I want to obtain now the computation rules with the Kohn-Radon-Nikodym derivatives. For instance, for any derivative, you have a chain rule. To obtain the chain rule, so this is the goal we have now. For this, we first extend the matrix trick of Alan Kohn. Namely, we will consider several phi 1, phi 2, several weights, phi n, and I denote by n the matrices n by n of m. And I denote by Eij in matrices. Let me see what I do here. Yeah, in matrices n over C, the usual matrix units. One at the intersection of one row and one column. Okay, and then if I have in matrices n over m an element which is xij, which is the same thing as the sum of xij tensor eij, ej from 1 to n, because this is the same thing as m tensor matrices n over C. And then I apply to this I just notice this thing. And then I do the following thing. Theta of xij, it's equal to sum of phi sub k of xij tensor of xkk. Okay, k from 1 to n. And again, theta is a normal semi-finite weight on the matrices over n. Okay, and now, using the previous lemma, it's easy to see that the sums of the form sum over k or plus or minus 1 tensor ekk are in the centralizer on theta. Just checking the other condition is put there. And then it follows that all ekk, that means 1 tensor ekk, they belong to the centralizer of theta. Of course, you add them and... Okay. Using the KMS conditions, we get that sigma t theta of x tensor ekk is equal sigma t phi k of x time tensor ekk. Is exactly the same thing as I did for two of them. And on the other hand, what we get that sigma t theta of 1 tensor eij, it's equal to d phi I over d phi j t tensor eij. Well, how to get this thing? You fix I and j. Fixing I and j, for instance, 1 and 2, then if you restrict only to these two projections, you look at the restriction of t to just 1 and 2. Then you get exactly the weight associated to phi 1 and phi 2.
Should be and J be interchanged?
I and J should be,
Ij, you have the 1, 2, and 3.
sorry?
Your UT
Yeah,
was image of the 1, 2, and 3.
yes, that's true. It's true. But now, if you have this, you look at, say, this is the situation with 4 matrices, right? And you look at the situation of 1 and 2, right? I fix I and J, so I fix them as being 1 and 2. Then what happens here is exactly as happened with phi1 and phi2 in the case of only 2 things.
Only 2 we defined that UT as sigma theta T of 1 tensor E21. That's how you defined it.
One quantum.
E21, okay. It is E21. You look in here.
So
So that,
I and J seem to be interchanged.
no, it's not reversed. Ah, you mean E21, that's okay, is GA. I thank you very much. So, it's okay.
No, it's the EIJ. It's EIJ, the same from I to J. So you don't reverse.
No, in here, it was this thing. Look, it was this thing, Masamichi. It was this thing, and this is 2, 1.
Yeah.
It's 2, 1, this one. So that Sundar was right. I have to put GA. Okay, so now I have also this thing in here.
If you apply T to be 0, then what happens? 1 tensor EIJ equal to 1 tensor EJI? No, there's no way. And the T has to move.
Maybe anyway, it's about this projection, right? So this projection, you call it, is the line over the row over number 2 and the column number 1. If you can write it as you like.
On the left side also you change the EJ. Sigma theta T
Second
of
indices stand for the dot.
Well, it's the same thing anyway.
Left hand, yeah.
On the left side, you make it EJI, please.
Yeah.
You just change the left side to EJI. Left side.
Here? Ah, yeah, okay.
Then also.
JI, yeah.
Now must be the objection.
So that it remains IJ and IJ
Then
here.
you have to change the.
No, that's the phi and phi.
No, then you have to change the cone derivative.
Anyway, you will check it alone. This thing is something very elementary anyway in here. It's about how you call this thing and something like this. It's no matter to. Okay, and then.
I don't use IJ. I use the list of this fees. So inside row, this matrix unit is indexed by
The only remark which is necessary here is that if you restrict to EII plus EJJ, you get what you get here, you get exactly the picture for 2 things. And now, if it is IJ or JI, I don't care too much indeed. Fine. And now, let's put a star in here for this relation. And now notice the following things. Notice that E1, 2 is equal E2, 1 star. Each way you want. If you prefer E2, 1 is equal E1, 2 star, I can put it so. From this and from there thing, it follows that d phi 1 over d phi 2 t is equal to d phi 2 d phi 1 t minus 1. Also, you have the same picture with n is equal to 3. You get that E1, 3 is equal to E1, 2, E2, 3. From this, it follows that the chain rule, namely d phi 1 over d phi 3 t, it's equal to d phi 1 over d phi 2 t times d phi 2 over d phi 3 t. Now it's nice to see the following thing also. If you have d phi 1 over d phi, it's equal to d phi 2 over d phi. That means this equality for every t. Then phi 1 it's equal to psi 1 is equal to psi 2. Here a small proof is necessary. Namely, you look at the, you look at this, and then you arrive at the situation d psi over d phi t is equal to 1 for every t. And then you have to show that psi is equal to phi, right? Okay. Now, to see this thing, you have this assumption. If you have this assumption here, it follows that sigma t tau of 0, 1, 0, 0 is 0, 1, 0, 0, because ut is equal to 1. Okay, now looking at the adjoint, I make the same thing with a 1 here, right? And I put both together, and I get this equality. Now, with this equality, it follows that this guy 0, 1, 0, 0, 1, 1, 0 belongs to M, the centralizer of M. So I may commute in this, so I have psi of x, it's equal to theta of x 0, 0, 0. But this is the same thing as theta of 0, 1, 1, 0 times x not 0, 0, and again 0, 1, 0, 1, 0. This is because I can move this thing here. And if I move it there, I get 1. So that, but now I apply I do the multiplication here. This will be theta of 0, 0, 0, x. I do the multiplication in here. Is that okay? Fine. And if I do the multiplication here, I get here psi of x.
So let's say that it should be 0.
Now, this equality is concerning this matrix and this one. Theta of this is equal to theta of this thing, because here I can move one of them in the other side, because this is in the centralizer, and 0, 1, 1, 0 square, it's equal to the identity.
No, I'm saying without the theta for the equation,
Sorry?
have x on one entry in one place and 2 entry on the other side. Before you apply theta,
Before I apply theta, is this one.
you know, right, 0 x. Here x should be at the 2, 2 entry.
Why isn't there one more entry?
I don't have any 2, 2 entry, because I have that theta of this and this is equal to phi of this plus psi of this. I don't go to any ut here. The ut
Okay, but if you go through with the computation,
is anyway the ut is this one, 0, 0, 0, so that it is equal to 1.
X was initially in the 1, 1 entry, but it will come to the 2, 2 entry, so it will become psi of X.
so the equation, see, if you use that equation, you will only get phi x equal to phi x. You will not get phi x anywhere.
No, it's coming to the 2, 2 entry. That's how? But how? Because you multiply.
Phi of x is this one by the definition of theta.
You can do 1, 1. That's right.
Then what I have, psi of x is this one by the definition of theta. Again, I'm sorry, is this.
It's okay.
There is no equality there, but it doesn't matter. It's this thing.
That is what I was trying to say, yeah.
So is that okay now? Fine. Okay. That was one thing. Now I leave it.
So are these statements true when one or two of them are not faithful, or this is only true if all the states or weights are faithful?
No. But you have to have the supports in a descending order in order to, you cannot make the derivative of a big thing with respect to a small thing. So you have to have the supports in the order. This is 1, for instance. This is the support of the other one, and this is the support of the third. And it follows exactly the same thing with trivial modifications. Okay, so let me see what is. I have half an hour more, right? Okay. So that having half an hour more, I will consider the following thing. In the 60s, and rather early in the 60s, 65 I think, Sakai proved a remarkable Radon-Nikodym theorem, saying for normal positive forms that if psi is less than phi, then there exists an operator A in M between 0 and 1 such that psi is equal to phi of AXA for every x. That was a remarkable Radon-Nikodym theorem, but on the other hand, a question remained without an answer, namely, when? For when? That means for which A is phi of A dot A less than phi of that phi. There was not an answer to this thing. At that time, no answer. But now, due to the Tomita-Takesaki theory, we can answer it. And this is the purpose of the next statement. Namely, is the following thing. Theorem. Let me first make a short definition. We have been speaking about analytic elements and of the analytical extension of the modular automorphism group. Well, that analytical extension was assumed to be to the whole complex plane. But we can consider also situations like this, we will see that A is analytic in a strip alpha complex numbers such that minus epsilon 1 is less than real of alpha less than epsilon 2, where epsilon 1 and epsilon 2 are positive, yes, positive, because I put a minus here, positive numbers. If you have an analytic extension of sigma t, t goes to sigma t of A, so you look at t goes to sigma t of A, and namely to it goes to sigma t of A, if this map has an analytic extension to the strip. And we will write the following thing. We will write A belongs to the domain of sigma alpha, alpha being a complex number, phi, if A is analytic in a vertical strip containing, I think it's I alpha. It's because of this thing, this one and this one here, right? Okay. Now, once you have this condition, we can write sigma alpha, sigma phi alpha of A. And this sigma phi alpha of A has the properties very similar to the analytic elements, but of course restricted to this strip, for instance, and so on. Okay, and then the answer to this question is the following. You have phi, an NSF weight on M, A, an element in M, and lambda, well, that's for lambda 0 infinity. Then the following assertions are equivalent. The first assertion is that phi of x of A, x star x, A star, is less than lambda square phi of x star x for every x in M. That means exactly this kind of condition. The second thing is that, well, I write it for NSF weights, but I will prove it just for normal positive forms. So x, if x belongs to n phi, which is M, if phi is a form, is finite, then x A star belongs to n phi, and norm of x A star, norm in the Hilbert space, is less than lambda times x sub phi phi. And the third condition is the answer to this question, namely that A should belong to the domain of sigma phi minus I over 2, and norm of the operator sigma minus I over 2 of A should be less than lambda. Now, for the proof, I will first notice that, well, if phi is a positive form, then this condition means exactly this, this inequality here. And this is obviously equal to this. So that I will say that I is equal to wi is obvious. Obvious by the definition of what means the form, the norm in the Hilbert space. It's phi of x star x power 1/2. So that you get immediately that 1 and 2 are equivalent. Okay. Now, let me prove that 2 implies 3. Okay. So that, let me first notice that if A is in the domain of sigma alpha phi, then P sub phi of sigma alpha phi of A, it's equal to, you may ignore the P sub phi, it's equal to delta power I alpha P sub phi of A delta phi minus I alpha restricted to the domain of delta phi minus I alpha and closure. And I used already this kind of equality, and I noticed that I announced then that this is not completely trivial. That means sigma alpha of A is delta I alpha, A delta minus I alpha. It's the closure of this operator, and I remember at the moment we wrote that book, me and Gido, we've been very careful to have all the arguments, everything to be proved. So we wanted to have a proof for this. And this is in lectures 9, 24. But on the other hand, it's something easily credible, namely that this thing is this thing in here. Okay. So let's prove now that 2 implies 3. From 2, it follows that there exists an operator T acting on H of norm T less than lambda, such that T of x sub phi is equal to x a star phi. And this for x in M. Okay, x in n sub phi. Now, assume that x belongs to a sub phi. That means m psi 0 in the cyclic case, which is n phi intersection n phi star. If you have this thing, you have the following thing. Tx sub phi, it's equal to x a star sub phi is equal to S of A x star sub phi. S means the adjunction. It's equal to S is sub phi, S sub phi pi phi of A, this is the multiplication by A, S sub phi of x phi is x star, which is in here. And this is further equal to, I put here j delta 1/2, and here I put delta minus 1/2 j. So what I get J sub phi delta sub phi 1/2 pi phi of A delta minus 1/2 J sub phi of A phi. Okay, that means that the operator delta 1/2 phi pi phi of A.
The last term should be x phi.
So up to here is okay? No, but up to here is okay? Okay, now the S sub phi is J sub phi, J delta 1/2, and the other S is delta minus 1/2 J. That was the question.
No, I'm just saying the last term for the next phi there you wrote a phi.
This one here means S sub phi.
After that,
That should be x phi.
you've written a phi, that should be x.
Oh, thank you. Fine, thank you. Thank you very much. Okay. Then it follows that this operator, delta sub phi minus 1/2, restricted to A phi, right, is bounded by lambda, with the norm less than lambda. And that means exactly the fact that A belongs to the domain of sigma minus I over 2 phi, and sigma minus I over 2 phi of A has norm less than lambda. That means exactly the statement 3 in there. And now for the, I will prove the fact that 3 implies 2. The 3 implies 2. We take an x in A sub phi equal to n phi intersection n phi star. Well, I take an x. I take an x in M if it is about normal positive forms. But this is just for the sake of the generality that I put it in this manner. Then I have that x star sub phi belongs to A phi again, but A phi is in the domain of S. That means this is M psi naught in the cyclic case, right? And this is in the domain of S. If it is in the domain of S, the domain of S is the domain of delta power 1/2. Okay. And now, using again the thing I wrote upstairs there, it follows with alpha is equal to 1/2 instead of a general alpha there. What I obtain is the fact that delta phi 1/2 p sub phi of A x star phi, it's equal to p sub phi of sigma minus I over 2 of A delta phi 1/2 x star sub phi. So you see, there are complications which are completely artificial when I want to work with weights, even in writing, because usually I could get rid of p sub phi and of everything. Okay. This is equal to this, so that S of A x star sub phi it will be equal to, well, will be equal to J, S of this will be J delta 1/2 of what I wrote here, right? Is that okay? So that S of this, I copy the other thing, and I have to put a J sub phi, P sub phi of sigma minus 1/2 of A, delta sub phi 1/2 x star sub phi. And so what I get, I get that A x star sub phi is equal to J sub phi S A x star. Now, okay. This is x A star phi, which is the S of this thing, it has a star of it, is equal to J sub phi P sub phi of sigma minus I over 2 phi of A, which is this thing here. This is G pi phi of sigma here. Okay. J phi S phi of x star phi. Okay, what I put here is the following. This is J times J delta power 1/2. J with J cancel, so I remain with the delta 1/2, which is here. Okay, and it follows that the following thing, that phi of A x star x A is less than the norm of sigma minus I over 2 phi of A times phi of x star x. Because sorry?
Normal square.
Squared, okay. Thank you. So it follows this thing. That means exactly what it was asserted in there. So that this result was not possible at the time of Sakai, because it is necessary expressible in terms of analytic continuation of something which did not exist at that time, the modular automorphism group. Thank you very much.